Hello, everyone. Welcome to the sixth and the final session of the day. And there will be 3 contributed talks in this session and 1 invited talk. So we start with the contributed talks. So just to remind that contributed talk is 25 minutes, including the question answer session. So we are looking forward to very good talks now. And Justin Lee is going to present first. So Justin, could you please share your slides? And he is going to talk about bit commitment scheme from non-local games. And Justin has graduated from McGill University, and he is now working in a company. And so he will enlighten us about this bit commitment scheme. Thank you, Justin. If you like, you can make it full screen. Yes, thank you. Over to you, Justin. Thank you.
All right, so I can start. Okay. Hi, everyone. So my name is Justin. Today I'll be presenting to you guys my thesis work for my master's in McGill under the supervision of Claude. So the title of the talk is Bit Commitment Schemes from Non-Local Games. Let's see. All right, so let's unpack the title a bit first. So there's 2 terms in the title, the Bit Commitment Scheme and non-local games. And so we would start by introducing to you what a bit commitment scheme is, and then non-local games, and then I'll show you how these 2 can be related and what we did with it. So first of all, for bit commitment schemes, you could imagine that there's two players, and one player wants to convey a message to the other player, but he doesn't want to announce the message directly. He wants him to know only the message after some time. So how can he do that? So this is what a commitment scheme can achieve. So first of all, let's say that on the left-hand side, there's a message that he wants to announce to the right-hand side, which is I am good. And so what he does is he conceals the message in some way and then send it to the second party. So that this is what we call a commit phase by concealing the message. And during this commit phase, what happens is the right-hand side, when he gets the concealed message, he will not be able to basically find out what the original message is. And over time, and so this is the first security property of a commitment protocol. It's called hiding. It's when the party that received the concealed message cannot find out what the original message is. So after some time, when he's ready to actually tell the other party what the original message is, the left-hand side would send some additional information to the right-hand side, for example, some keying material, whatever. And once the right-hand side gets the additional information, he will be able to compute and obtain what the original message is. So this phase, this is the second phase of the commitment protocol. It's called the unveil phase, when the person that wanted to convey the message sends this additional information. And now we reach the second security property of a commitment protocol. It's called binding. And what that means is that whatever information this left-hand side party wants to send to the second party, the second party can only compute and get the original message. So it means that if he sends some different key materials, he should basically detect that there was a change in what he wanted to convey. So in the end, he should be able to always get the original message, which is I am good. And in the case where the commitment protocol, the party wants to only convey 1 bit of information, so 0 and 1, we call that a bit commitment scheme. So to recap, the bit commitment scheme has 2 phases, which is the commit phase by concealing message, and second phase is unveil phase, when he unveils what the original message is. And it has 2 property, which is the hiding property, where the second party cannot find out what the original message is without the additional material. And the second property is binding, where this guy cannot actually change what the original message is once he sends the concealed message and the additional information. Okay, so now we can move on to the non-local game. A non-local game is a tool that we can actually use to demonstrate the difference between classical resources and quantum or non-local resources. It's usually defined for a 2-player game. So there's 2 players and also there's a 1 verifier. And we can quantify the game in terms of mathematics. We can define the set of all inputs that the verifier would ask the players. So here I denote them as X and Y, and also the set of outputs that the player can answer back to the verifier, which is here A and B. There's also usually a pi, which is called a promise in terms of like the promise on the set of inputs that the verifier would ask. For example, could be that all the questions that the verifier would ask would be odd or even. And finally, there's always a winning condition for the game where the verifier, once he asks the question and gets the answer back, he can compute this function and say that whether or not the players have won a game or not based on the output. So let's illustrate that in the following diagram. So, and actually there's one crucial detail that I forgot is the players, when they play this non-local game, they actually separate it, either space-like or some other way to separate them so that during the game, they cannot actually communicate between each other. So let's say the verifier asks them questions, they cannot tell each other what are the questions that they got. But before the game starts, the players can actually get together and think of a strategy in terms of how they can actually maximize the winning probability for the game. And so let's say the verifier samples some questions and asks each player individually a question. And the players, after some time, they answer back based on the input usually. So let's say Baby Groot really want to say that I'm good, because that's what he knows how to answer. And Baby Yoda is smart enough to know what the answer should be. So he answers B, for example. And then now the judge or the verifier would use the winning condition function that I mentioned before to check whether or not the player has won the game. But since let's say that the output set is always a bit, and since Baby Groot has answered I am good, which is not quantified, then they have lost this game. And as you can see, maybe Baby Groot is not a really good player in this kind of game because he will always lose the games. We can further quantify a non-local game by the values of the game. So here, the first term with a subscript C is basically the classical value of a game. It's when the players are only able to share classical or local resources. And for local values, we can actually think in terms of deterministic strategy also, because they are actually equivalent. And for the second term here, this is the quantum value of the game. It's when players can actually share quantum states and they can operate on their individual qubits in order to answer back on the questions. And when a non-local game has a quantum value of 1, meaning that if players have a proper quantum strategy, they can always win the game no matter what the input the verifier has asked, then we call this games pseudo-telepathy games. And we can also generalize what the definition of the non-local game in terms of n players instead of just 2 players. And now we just have a set of inputs for each n player and a set of output for each n players again. And the winning condition would be in terms of all the input and output of the players in this case. And here's a list of some other specific non-local game that I found. For example, the CHSH game, the Guess Your Neighbor's Input game, Merman JSA game, and Magic Square games. I put an asterisk in the first 2 games because these 2 games actually doesn't have a quantum winning strategy, meaning that the quantum value of those 2 games are not 1. But if the players can share the so-called PR box, which is a non-local resource, they can actually win the game. Whereas the third and fourth games, there's a quantum winning strategy. So they can, if they share the proper quantum state, they can actually win the game 100% of the time. All right, now we can go on to the main result. So what have we achieved in this work is that we actually devised a protocol to construct a classically secure big commitment schemes using any non-local games, but more specifically, any pseudo-telepathy games. So non-local game that has a quantum winning strategy. And secondly, to prove that our big commitment scheme using this protocol is classically secure, we have also defined a non-binding game to prove the binding property of this protocols. And a bit of a motivation on why we actually want to do that. So like I said, the big commitment scheme that's resulting of this work is only classically secure, but if the players actually share the proper quantum states, they can actually break the binding of this commitment protocol, meaning that it's not secure quantumly. And one of the motivating reason why we do this is for zero knowledge, because big commitment scheme is a building block for building more complex cryptographic protocols such as zero knowledge. And usually for simulating zero knowledge is usually the verifier that simulates the global transcript of the entire protocol. But with this quantum breakable big commitment schemes, the individual players can actually simulate their own input and output and achieve what's called a quantum simulatable zero knowledge, even in the relativistic settings, where each player has to talk with one verifier next to each other. So now I would introduce even more core components in order to arrive to the final protocol to construct the big commitment schemes using a game. So first of all, we're going to talk about parallel repeated non-local games. So I've shown you what a non-local game is, played with 2 players, all n players. And now when we talk about parallel repeated non-local game, it's when the same game gets repeated k rounds. And the caveat is that the players, they would basically just think of playing the game over and over again, but they only win the entire parallel repeated non-local game when all k rounds of the input output actually win, like it's a winning condition. So if any of the rounds one of the players slips off and answer back a wrong answer, then they will lose the entire parallel repeated non-local game. So the conditions are more strict for them to win the whole thing. And then next, I'll talk about anchoring transformation, which is from a paper. This is a relatively easy transformation for a non-local game. And what they do is that the verifier, each time he samples, basically he checks the set of all possible inputs for the players. And for each input that he samples, there's a probability that he will anchor the inputs, mark it as a special symbol like alpha. And if for any instance of the anchor game, the verifier has sampled an anchor input and given to a player, no matter what answer the player answered back, the verifier will just accept that round of the game, meaning that the players will win the game for free for that round if there's an anchor input. So you might think that this would actually make the game much easier, and that is true. But so basically with this transformation where each input gets anchored with a probability, the players only get to play the original non-local game with certain probability. But after this transformation, we get this nice theorems such that basically the quantum value and the classical value of the game improved a bit. But if the quantum value of the game was already 1, then it actually doesn't change anything because 1/4 plus 3/4 is still 1. And the more important thing is that if the classical value of the game was not 1, meaning that the player with classical resources cannot always win the game, then if we anchor the game and we also play it in the parallel repeated manner, meaning that we repeat the game k rounds or however many rounds, then we will see that the probability of them winning the entire thing actually is bounded. We know that it's still less than 1. And we already know this result from the Raz parallel repeated game theorem, saying that if there's in the 2-player case, and when we repeat the game k rounds, then the winning probability of the game is still less than 1. But with this anchoring transformation, we can actually extend this definition to n-player case, which is what we want. Now I'll talk briefly a bit about the strategies. So in terms of determining strategies, there's a very simple example in the beginning that I have shown is when the baby Groot, no matter what input he gets, he'll always answer back, I am Groot, which is a determined strategy, meaning that it doesn't matter what the input is, he will always answer back something. But it can be even smarter. Basically, if the input is something, then with the determined strategy, you can answer back always the same thing, but based on what the input is. And we can also talk in terms of local strategies. It's when players share this determined strategy, but they can also use share random resources. So let's say that they share coins and they can toss it, and they can actually use the input that they get and also the share randomness in order to compute what the answer they will answer back. That's what we call a local strategy. And if they actually share quantum states and they can actually use the measurement result of their own qubits along with the input to answer back, then we call this a quantum strategy. Now, I will define one of the final thing that we need to get to the main result. It's called the exclusion set. So like I said, for a non-local game, the classical value usually is always less than 1, meaning that players will not be always win the game on some inputs. So for any given determinate strategy that's classical, there's always some input in that the players would answer back in the wrong answer. And so we define the exclusion set in terms of the strategy that's chosen and also the set of input that using this strategy would make the players lose the game. And since there's more than one determinate strategy for the game, and also for the same set of inputs or exclusion set that the players would lose on using those strategies, there's actually more than one strategy to arrive to the same input. We can actually quantify or group the set of determinate strategies by this exclusion set or the set of inputs that the players will lose the game using those strategies. So let's say that, for example, the first exclusion set is only input 1, and the set of strategy later on is that if players use those strategies and the input is 1, then they will lose the game. Then we can actually group the strategies by this exclusion set. So now I can actually present to you guys what the final protocol would be. In order to build a big commitment scheme using a pseudo-telepathy games, we'll do a couple transformation first. So first, we will anchor the game, like I mentioned before, and actually for the players to commit to a final bit value, they would need to actually commit to a matrix of bit values. So basically we will anchor the game, and then we'll play the game k-square rounds. And for each round of the game that they play, they will try to commit to one single bit value. And the condition of this bit matrix is that each k rounds of the game that they play, the XOR of all those bit values should be or needs to be the same as the final bit value that they want to commit. So that means that they would try to commit k-square bit values, and k of them should sum up to the final bit value that they want. And if that's not true, then, well, you can guess that that commitment is invalid. So now let's see how they can actually commit to a single bit value for each round of the game that they play. So what the players would do before running this protocol is they would look at the game. They would actually find out all the determinate strategy that they can use, or the optimal ones that they can use to win the game. And then they would, for each strategy, they would find out what the exclusion set for them is. And then they would bipartition this exclusion set on 2 sides. As long as one of the sides is not empty, this partition is fine. And based on the exclusion set, we can actually see what are the strategies that correspond to those exclusion sets. So then for each round, they would choose a bit value from this bit matrix. And based on the bit value, either 0 or 1, they would choose an exclusion set from either side. So if it's 0, then they would choose one exclusion set from this side. If it's 1, they would choose one exclusion set from this side. And based on the exclusion set, or the set of input that they will lose a game using any strategy in that exclusion set, they will agree on a single strategy that they will use for that round of the game. And they will repeat that for like any round. And then now it's basically the same as the non-local game that I defined. The players would play the non-local game in this manner. The verifier would sample some input for each player. He will ask the input to all the players, basically. And remember that they have chosen a bit value to commit for that round. And based on that, they've chosen an exclusion set, which means they also chosen a strategy that they use. Then they can use that same strategy to query what the answer should be based on their input. And once they get the output, they will answer back to the verifier. Now, there's a problem with this, is that if the verifier actually knows all the input outputs of any rounds, there's a good chance that he can actually find out what the strategy the players have agreed on. And if he can find that out, he can actually find out, there's a chance that he can find out what the exclusion set is, then maybe he can also guess what bit value they're trying to commit on that round, which will break the hiding property of the commitment protocol. So what we want to do is actually to hide a single player's output in order for the verifier to not be able to guess everything. So what we do is we designate one single player to run a separate commitment protocol that is actually quantumly safe to hide the output of his round, basically. So again, now what happens is the verifier samples the same questions, but with an additional string that he chose. He sends that additional string to the player that is going to run the commitment protocol with the additional player. And now here, the designated player and the additional player share a matrix of strings, and they will basically, based on the R and the input that he gets and this U, he will commit his answer and send it back to the verifier. So if this commitment is actually quantum safe, then the verifier would not be able to guess or find out what the answer this designated player want to answer. And after K-square rounds, when we need to actually unveil everything, we let the additional player to unveil everything. So the matrix of bit value that he wants to commit, the shared string that he had with the designated player, and also how we partition the exclusion sets. And with that additional information, which is the shared matrix, the verifier can actually compute all the answers or unveil all the answers that the designated player was hiding. And with that, the verifier gets to verify if for each K-square round, the players have actually answered correctly for that game. And if the players actually answer correctly for all K-square rounds, and then the verifier will accept that commitment. If not, if any of the rounds of the game the players have answered wrongly, then he would say that the commitment was false. So a bit on the non-binding game. The non-binding game that we've defined is exactly the same setting as the protocol that I just showed you. The player would play using the same strategies. They would find an exclusion set, they would decide on strategy to run, and then they will answer back. But instead of the final additional player unveiling what they wanted to commit, in the non-binding game is the verifier gets to choose a single bit value and force the players to unveil that. It doesn't matter what the player wanted to commit in the beginning. He will still force that value to the players and let the player try to unveil it correctly. And of course, if they are not cheating and they're running the protocol correctly, then they would not be always able to unveil that false value. So we say that the game is binding if for all the possible value that can unveil, they can only unveil it with certain probability. So that's it for the talk. Thank you.
Thank you very much, Justin, for a very nice talk. Any questions from the audience? You can write the question in the chat or on Discord. So how vulnerable this scheme is to losses, and like if there's some adversary involved in between and some of the bits they get exposed, then how safe it is? If
there's some adversary, like if the player want to cheat the protocol?
Yeah, if a player is cheats or the channel reveals the value to another third party.
Oh, so you're saying there's like additional party involved, and then he unveils what he wants to answer to the other player?
Yeah.
Yeah, I don't know. Like, we don't consider like outside player in this commitment protocol here. Okay. It's only the player involved and the verifier, and basically the players against the verifier and the verifier against the players. Okay.
And you had to yeah. Please go on.
Oh, I was just saying that each other want to find out what they want to achieve at the end. So the verifier want to find out what they want to commit, and the player want to basically trick the verifier to think that they're committing something, but then they unveil something else.
Okay. So there was another question which has been asked. Could you please comment on how to decide the exclusion list from the list of games G?
The list of exclusion sets. Yeah. So how to partition them? Yeah. So like I said, this is actually not strict. So as long as there's non-zero exclusion set in one side, this should actually work fine.
Okay, thank you. So thank you very much for a very nice talk. So you can still ask your question in the Discord channel, and he may be checking those, and he will answer there. So thank you, everybody. So let me stop the recording and